All right, welcome back. So today we are going to try to solve this problem called climbing stairs. Pretty popular problem. So it's listed as easy, and you'll see why. But I still want to go through this question because it shows you the way you should think about problems. It gives you, I like to use this example a lot. So you'll see why. I don't want to give you any spoilers, but let's go to it. So here it says you are climbing a staircase. It takes n step to reach to the top. Each time you can either climb 1 step or 2 step. How many distinct ways can you climb to the top? See, just given this problem, the first time I heard it, I was like, wow, that sounds really, really hard, right? And it's funny because I was able to solve another question, which was actually very similar to this question in terms of the implementation, but I just didn't know. So here's why I stress again and again. It's not the algorithm, it's not the data structures that are hard. It's more about understanding the problem, mapping it into a solvable algorithm, right? So let's think about it here. So how many steps can I climb to the top? Well, every case you have either 1 step or 2 step that you can do. For example, let's go to the iPad. Imagine there's 1, 2, 3, 4, 6 steps, right? So then, given that the bunny is here, does it say bunny? No, it's not, but okay. You could do 1 step or 2 step. And then once you're here, for example, let's say you did 2 step, and then 2 step you have 1 or 2. And then when you were at 1, you were 1 or 2 also. All right, so that's pretty much like, it's kind of hard to think about it this way, but when you think about, okay, how do I record every time I'm at somewhere? How do I know how many steps it takes? So for example, let's say the bunny, what I meant is, let's say the bunny is right here. The bunny is right here. How many different ways is there to reach here? So I'm pretty sure the number of ways to reach here is the same as the number of ways to reach here, because it's still just 2 step, 1, 2 versus 1, 2. So these numbers are kind of similar. So how would we solve this now? So now that we know these two are kind of similar, what we can do is we can think of it this way. Okay, imagine you have a bunch of stairs. 1, 2, 3, 4, 5, 6, 1, 2. Okay, now we have 7. But what we can do is, given that I know I can go here, like I'm the bunny, I can go here, or I can go here. So then, given that if my bunny was here, how many steps would it take? How many possibilities can I have to get to here? And then if the bunny was here, how many possibilities do I have to get to here? So what would be the answer if suddenly you have that function already written, right? So remember when I said, oh, imagine if you already have the function written, and then how would you solve your problem? Then that is something very familiar. It's recursion, right? So basically this is kind of simple. It's actually just whatever, like for example, let's see, like the answer for n, imagine n stairs, is actually the same as if the answer for n minus 1, how many ways can I go there, plus the answer of n minus 2, right? Because we know that there's 2 different ways. The first way is we take 1 step, and the second way is we take 2 steps. And then given that we have these 2 positions, can we solve the same problem? We can, because we have this function, and we imagine that it's already written. And then with that, what we need is a base case. Like for example, if n equals 1, then we know that's equals to 1. And then that's the base case, right? So basically that's pretty much recursion, and let's just write it down. So let's go to the computer. So I think pretty much the answer should be this for recursion. So recursion, very, very simple. Let's see. Just a minute. Okay. So we know that, okay, If n equals 0, then return 0. If n equals 1, return 1, right? And then what you want to do is you return the same thing, climb stairs for n minus 1, plus self climb stairs for n minus 2. Let's see if that works. Let's just run the code. Should this be 1? Oh, yeah. So if you have no stairs to climb, it's still one way because that way is you doing nothing. Okay, cool. So that's 1. And then for 1, the only way you can climb is 1. Okay, cool. So that's pretty much it. And then that runs. But if we submit it, we'll see that it goes over time. Yeah. See, time exceeded, but there's no errors in between them. So if you look at this, you would realize that it's very familiar. And why is it familiar? Because this is the same as calculating the Fibonacci sequence, right? So there you go. Now, if you knew that, then it would have been really easy, but it was the mapping the problem into the actual algorithm that was hard. I mean, it seemed pretty easy because here I just explained it, but in the end, it's actually really easy in terms of the algorithm, but it's the part of translating the problem into an algorithm or data structure that is difficult. All right, so I'm pretty sure most of you know how to do the Fibonacci sequence. So you can just turn it into the iterative version, which is very simple. You do it, if n equals 1, you return 1. I think if n equals 0, return 1 also. And then you have the first number, you have the second number, it's usually 2. And then what you do is you just iterate through them. And then the third becomes the second number plus the first number. And then after you get that, the first becomes the second, and the second becomes the third. And then you return the second at the end, right? Yep, and that's pretty much it. And then, yeah, it's actually just the Fibonacci sequence. And yeah, to understand, we can actually pretend we don't know it's the Fibonacci sequence and go through this. I feel like doing this. All right, let's go back to our map. So remember we had the Fibonacci sequence. Oh, sorry, let's pretend it's not Fibonacci. We found the recursion, and then that's the answer. And then if you think about it, for n, you need to compute n minus 1 and n minus 2, right? And then this is to calculate n. Each circle is a function call. And then for n1, you need n minus 2 and n minus 3, right? And then for n2, you need n minus 3 and n minus 4. And then it just keeps on going. And then if you know the math, if you do 1 plus 2 plus 4 plus 6, sorry, plus 8, you'll realize that the number of times that these are called, it's going to be 2 to the n, because every time you call a function, you call 2 more, and then it does that n times, so then that's 2 to the n. So O of 2 to the n is the time complexity for that. So, and then we realize that if we computed n minus 2, how come we have to, let me put it red. If we computed n minus 2, how come we have to compute it again? Or n minus 3, why do we have to compute it again here? Or even, actually, yeah, that's it. And then let's see, like n minus 4, and then here would be n minus 4. Like, we keep computing the same thing. So it's a little bit silly when you think about it. Which is why what we will do, oh, by the way, and then the height of this would be n, because we do it n times. Yeah, so basically you don't want to repeat this. So what we can do is we can have a data structure that records it for us. Imagine a data structure, right? For n equals 0, n equals 1, n equals 2, n equals 3, n equals 4, n is 5, and then 6. And then here we know it's 1, here we know it's 1, and then 2, we know that it means we have to add the 2 previous ones, right? It's 2. And then 3, because we already calculate these guys, then we know it's only adding those two. So it's 3. And then because of this, we don't need to recompute. This is called memoization. So we don't need to recompute the numbers that we already did. We memorize them into like an array. The only hard part is to understand where to start your computation. Here it's easy because it's only one dimension. Sometimes in dynamic programming, it's multiple dimension, right? So then now you have as O of n time instead of O of n squared. This is for the time complexity. And then for space, it's also O of n because you have n numbers here. So 5, 8, and then 13. Right? Because you just calculate by looking at your 2 previous terms. But then the thing is we could do even better in terms of the space complexity, because every number we compute, we don't need to look at anything beyond the first 2 numbers. Like for example, if I'm calculating for this guy, all I need is 3 and 2. I don't need anything that's here. I don't need this. Every time I calculate a new number, I just discard the old ones because I never look at them again. So that means we only need 2 variables. And then this becomes first, this becomes second, and this becomes third, right? That's why we have third equals second plus first. So that's how you usually do dynamic programming. First, you have a recursion. Well, it's not always, but usually what I do is I have a recursive function, and then I solve it in better time by having an array or like a data structure that keeps I memorize my answer. And then you could save on space by realizing that you don't use all of this space. You only use a few sections of this space every time. So like I said, good framework. You have a recursive algorithm. You turn it into iteratively so that you can memorize the information. So then you save on time. And then once you have a lot of space, you could look at what values you actually look at into this array or this space that you added. And then you could minimize it by removing all the ones you don't need, just like we did here. Anyways, that's pretty much for this question. And yeah, I hope that was good. And yeah, see you at the next question.